right, there's one more formula for curvature in your text. It's actually given on page 865. And as with the other formulas, I'm not concerned that you have it memorized. I don't. I'm concerned that you know how to use it, but I'd also like you to know how to derive it. Okay, so it's for if we have something where y is a function of x. So this would be a curve in 2 space, but where y is just a function of x. Now, if I want to find the curvature of that, I would want to write that as a vector function. So I would go from this to r of t. Now, ordinarily, I would go to a curve in 2 space. If I want to, though, I can go right to being in 3 space, and I could just say it's t f of t 0, and then I can apply my other formulas for curvature, but I'm going to get things in terms of the derivatives of f. Okay, so that formula, again, I'm not concerned that you have it memorized. I'm not even bothering to write it down, but that formula is given on page 865. They do talk you through a derivation of things, but basically just apply the other formulas for curvature to this. I'm going to leave that as an exercise for you to try. I would encourage you to do that, and if you have questions, ask me about it in office hours. If, rather than going right to 3 space, you chose to just go to the curve in 2 space, then you would have to embed that in 3 space if you wanted to use the formula for curvature that involved the cross product. So then we'd be talking about r tilde. I think it's easier to just skip right to 3 space. That way you haven't already used the name r for a curve in 2 space. You can just call this your r of t and derive that formula. All right, so next thing I want to talk about is, I know if I have a smooth curve, and this could be in either 2 space or 3 space, but let's talk about in 2 space for just a moment. If I have a smooth curve, it's going to be oriented, and if it's smooth, t of t, which is just r prime of t normalized, is always going to exist, and in fact it's going to be a continuously varying function of t. Okay, so at every point on the curve I would have a unit tangent vector. So it would have the same direction as my derivative, and I would just normalize it to make it a unit vector. Okay. Now, once I have that direction, if we're in 2 space, that gives me then a semi-unique direction that would be normal to the curve, that would meet it essentially at a right angle. Here it would be either this direction or this direction. So once I have one direction that's perpendicular to the unit tangent vector, the opposite direction is also going to be perpendicular to that. Now in 3 space, if I have a curve and I have a vector that's, let's just say this was my unit tangent vector in 3 space, there are going to be infinitely many vectors that would be perpendicular to that. So I don't have a semi-unique direction there. But what we're going to do is we're going to come up with a formula for finding a vector that we're going to call the unit normal vector. In 2 space, it will have to point in either this direction or that direction. And a nifty consequence in 2 space is that in 2 space it always points to the concave side of the curve. So my normal vector here would be pointing in. Over here, my normal vector would be pointing in like so. So over here, it's on this side of the curve. Over here, it's on the other side of the curve. There would have to be some point in there where the unit normal vector didn't exist so that it could sort of change sides of the curve. But how do we do that? So I want to try to find a vector. If I can find a vector that is perpendicular, so not just orthogonal, but perpendicular would be my preference to the unit tangent vector, then I can normalize it and I will have a unit normal vector. So how do I get that? Well, this is where I refer back to a theorem that we had in the last section that I said you should vow that you will remember this. And so when I say we had a theorem and you vowed to remember it, You don't say, oh, I forgot. Probably right now you're saying, oh, I forgot. That's what usually happens. Okay. But notice, t is a unit vector. So its magnitude is always constant. What that means is it's orthogonal to its derivative. So if that derivative is not 0, it will be perpendicular to the unit tangent vector. Okay. So since the magnitude of t is 1, I know that t of t dotted with t prime of t is always going to be 0. They're always going to be orthogonal. If this is not the 0 vector, then they're actually perpendicular. So the unit normal vector won't always exist. If there's a place where this is the 0 vector or where this doesn't exist, then we're not going to have a unit normal vector. But we can define n of t, the unit normal vector, is just t prime of t normalized. Okay. So the unit tangent vector is guaranteed to exist if we have a smooth curve. The unit normal vector is not guaranteed to exist if we have a smooth curve. It will exist if t is differentiable and if t prime is not 0. Now, it's going to be most of the time, but there will be some isolated points where the unit normal vector doesn't exist, and that's okay. Like I mentioned, in 2-space, we essentially have two possibilities for the direction that the unit normal vector could point in, and in 2-space, n of t points to the concave side of the curve. But this definition for the unit normal vector applies in 3-space as well. So in 2-space, we're choosing between two possible directions that are perpendicular to the unit tangent vector. In 3-space, we've got infinitely many possibilities, but this will pick out one of them. Okay, so let's see if we can't just find ourselves a unit normal vector. Okay, so I'm going to go with r of t equaling t squared. So I know that's my basic parabola. And what I'm going to try to do is I'm going to find the unit tangent and the unit normal vector at 0. Okay. Now, r prime of t is 1, 2t. Okay. So the magnitude of r prime of t is the square root of 1 plus 4t squared. So t of t is 1 over root 1 plus 4t squared, comma 2t over root 1 plus 4t squared. Okay. Now, t of 0 is just going to be 1, 0. Okay. That's actually pretty easy to see by inspection, because I can see that at this point, I know we have a horizontal tangent line, so I know I've got to have a vector that's purely horizontal. It's got to be a unit vector, and it's got to be consistent with the orientation, so it's got to be pointing to the right. So that's an example where here the algebra that we just did confirms what we should have been able to figure out geometrically anyway. There's my t of 0. Now, similarly, I should be able to figure out by inspection what n of 0 is, because it's got to be perpendicular to t of 0, so it's got to point either straight up or straight down, but we said in 2-space it has to point to the concave side of the curve. So it's going to point straight up. So I can see by inspection n of 0 should just be 0, 1. What I'd like to do is just confirm that. Okay. So let's do the calculations. Now, if I'm calculating n, I need to calculate t prime. So, can't have 0 plugged in before I take a derivative. If nothing else, I'm showing you that calculating the unit normal vector is tedious, because always calculating the unit normal vector, if you're not just doing it by inspection, which can be very simple, If you're not doing it by inspection, it involves taking the derivative after you have normalized. So you've got messy component functions. Okay, I'm just going to rewrite t up here, but I think I'm going to rewrite that as just 1 plus 4t squared to the negative 1, so that I can use the chain rule rather than the quotient rule. And then the second component, I'll just use the quotient rule, but I'm going to rewrite this as 1 plus 4t squared to the 1/2 on the bottom. Okay. All right, so there is my t of t. T prime of t will be negative 1 plus 4t squared to the negative 2, chain rule, times an 8t. Okay. Let's see. Here we'll use quotient rule. So low, 1 plus 4t squared to the 1/2. D high, the derivative of 2t is 2, minus high, 2t. D low, oh, I'm going to run out of space. Rats. Okay. I'm going to give myself some more room. Okay, t prime of t. We said here we had negative 1 plus 4t squared to the negative 2 times 8t. All right, so here we're using quotient rule. So 1 plus 4t squared to the 1/2 times 2 minus high is 2t. D low, we're going to get 1/2. 1 plus 4t squared to the negative 1/2. Chain rule times an 8t. And then all over the denominator squared is just 1 plus 4t squared, because the denominator was a square root. So let's get this in a slightly more user-friendly form. Here, I'm going to have negative 8t over 1 plus 4t squared in that first component. Let's simplify our second component a little bit. Let's see, that's 2 times the square root of 1 plus 4t squared. Here my 2 and my 1/2 are going to cancel, but here I've got a minus 8t squared over the square root of 1 plus 4t squared, and then all of that is over 1 plus 4t squared. Not crazy about the complex fraction. However, I'm actually at a good place to stop simplifying, because if my goal was to find n of 0, I know I have two things left to do. I need to normalize this, and I need to plug in 0. But I can do them in either order. Okay. It's totally fine to plug in a number before you normalize. It's never okay to plug in a number before you take the derivative, because as soon as you plug in a number, you don't have changing functions anymore, so you don't have a rate of change anymore. But it is okay to plug in before you normalize. So if you're asked to find a unit normal vector at a particular point, rather than find a formula for the unit normal vector, it's almost always going to be easiest to plug in first. So if I were going to be finding a formula for n of t, I would take some time to simplify this, because I then have to find the magnitude, and oh, it's going to be a mess. And this was a pretty simple function. Okay. But I can say t prime of 0 is, if I plug in 0, this becomes 0 over 1, which is 0. I checked just to make sure the denominator wasn't 0, to make sure that it was defined. Okay, then over here, we're going to have, let's see, this is going to be 2 times 1 is 2, minus 0 over 1. Oh, that was lovely. Okay, so we get 0, 2. So the magnitude of t prime of 0, I can see by inspection, is just 2. And so n of 0 will just be 0, 1. Scale each of those components by a factor of 1/2. Okay. And that confirms what we thought it should be. Okay. So I wanted to show you that for two reasons. One, so that you can see it actually does do what I said it was supposed to do. Two, so that you could see that it really does get pretty tedious to calculate. Okay, so it's a nifty concept, but calculating the unit normal vector can get pretty tedious pretty quickly. So if you're asked to calculate a unit normal vector and you feel like, oh my goodness, I'm getting bogged down in calculations, it's not necessarily that you've made a mistake. It just is an inherently tedious process.